Welcome back. This is the second video after an introduction video that was centered on the review of limits. Okay, and the topic in this video is section 7.6 on improper integrals. Again, if you're interested, see the intro video on what does the limit notation mean. So this is a topic that you would have covered in your previous calculus course, either in high school or in Math 0110. We then talk about limits to infinity. What do those mean? And reminded you of things that you would have done in that previous calc course. We played with some tables of values to get a little bit more of an intuitive feel for what limits to infinity mean. And then played with some algebra games to put in these middle steps for all the statements in red here, all the middle steps in green we really shouldn't be writing. But if you're desperate to show middle steps for your own benefit, not for marks, like don't write this stuff for marks. It's kind of like in many courses writing this type of thing is a way to lose marks. But if you want to show middle steps for yourself, the green stuff is I think helpful for a lot of people. If you like graphs, there's other ways you can understand limits, and that was discussed inside that intro video. So check it out if you're interested. What we're going to do in this video is focus on kind of the operations that you're going to do for improper integrals. Up until this point, every integral that you've done, or rather every definite integral that you've done, has had this form. It's been an integral from a to b of f of x dx where a and b are numbers. That formulation is called a proper integral. An improper integral, there's actually several types of improper integrals, and we're only going to look at one type. The type of integral where one or both the bounds are replaced by infinity. And as tempting as it is, infinity should not be treated as a number. It is different. Now, sometimes the top bound is infinite. Sometimes the bottom bound is negative infinity. And sometimes both bounds involve infinity. So we could have an integral that goes from x equals negative infinity to x equals positive infinity. If you flip back to section 6.5 and think about what these statements mean in terms of areas, you get an interesting picture. A picture that isn't, I guess we don't need to go through it, and it's not part of the main aspect of the lessons and other videos, but I will touch on it later. I'll make more statements about areas. There are good reasons to be afraid of working with infinities if you don't know what you're doing. In other courses, a lot more time is spent grappling with infinities and grappling with different types of indeterminate forms for limits. We're not going to do any of those things. We're just going to launch right into dealing with infinities and integrals. We will be a little bit careful, at least with notation. So the integral from a to infinity of f of x dx, the way that we're supposed to write this carefully is to say, well, I'm going to take the limit as b approaches infinity and then integrate from a to b. What this means for us in terms of the operations that we do to solve a problem. This is now a three-step procedure. In the first step of the procedure, we're going to find the general antiderivative of little f of x. In the second step of the procedure, we're going to take that general antiderivative, or we're going to evaluate it on the bounds, on the top bound, on the bottom bound, and then we'll subtract. And then the third part of our procedure, the third part of our set of operations, is we'll take a limit of that. We'll take the limit as b approaches infinity of that expression. I'll do a bunch of examples going through that process. Sometimes when you take a limit, a number comes out, like 0 or 3 or pi or e to the 2, but a number appears. And sometimes a number does not appear. You get infinity or minus infinity or something worse than that. In situations where you get a number coming out, we say that the integral converges. So if the limit exists, limit of the resulting object from the antiderivative being evaluated, if that limit exists, if you get 5 or 2 or 0 or -8, then the integral is said to converge. Some vocabulary. And if it doesn't exist, if the limit goes to infinity or minus infinity or something worse than those, then instead of saying that the integral converges, we say the integral diverges. So a particular terminology. In the previous slide, we had the conversion for the integral from a to infinity of f of x dx, where we said it was the limit as b approaches infinity of that expression, replacing the infinity with a b. Now what happens if we're going from minus infinity to b instead? So if our lower bound is a negative infinity, what we do is we replace the negative infinity with a, and then we take the limit as a approaches minus infinity. So again, we split it into 3 steps. Step 1, find the antiderivative. Step 2, evaluate on the bound. Step 3, take a limit. And the same vocabulary is attached to this. If that process gives you a number, then we say that the integral converges. And if that process spits out infinity or minus infinity or something more horrible than that, then we say the integral diverges. So let's look at some concrete examples next. First concrete example is we're asked for the integral from 5 to infinity of e to the negative x dx. So I'm going to write this out in those steps I was talking about before. Well, actually, before doing the steps, let's use the right notation. We should convert this to a limit as b approaches infinity of an integral from 5 to b of e to the negative x dx. Now step 1. We're going to find capital F of x, which is the antiderivative of the original function, e to the negative x. We do this by doing the substitution. I want to use w, but I won't. I'll hold back. U equals negative x. So if we take the derivative, du by dx, we get -1, then rearrange, and dx is the same thing as negative du. So we'll go in and make all the substitutions. We have e to the u times negative du. So negative integral e to the u du. Antiderivative of e to the u is e to the u. So we have negative e to the u. We have a plus c, but because step 2 will involve bounds of integration, we don't have to worry about the plus c. The plus c will cancel. We're just going to replace u with what it was when we did the substitution. I'm going to replace it with negative x. Okay, step 2. Evaluate capital F of x on the bounds. So I have capital F at the top bound, so capital F of b minus capital F of the bottom bound, capital F of 5. So when you plug b in, you have negative e to the negative b. When you plug 5 in, you have negative e to the negative 5. Now we are subtracting a negative. The negatives are going to cancel. We'll get a positive. So negative e to negative b plus e to negative 5. And then that is the end of step 2. Now we go to the new step for this section that we haven't had to do before, is we take this result and plug it into the limit. The integral is now replaced with that stuff that we just found, negative e to negative b plus e to the minus 5. Okay, we're taking the limit as b approaches infinity. So we have negative e to the negative infinity. We're just supposed to write 0 for that piece. And then the second piece There's no b in e to the negative 5, so the limit of a constant just stays as a constant. We just get e to the negative 5. And that is our answer. Okay, and if you want to know why that first term turned into a 0, check out the intro video that came before this one. Okay, second example. Integral from 5 to infinity of e to the x. Well, all that changed is the negative x turned into a positive x. The bounds are the same. We're going to go through the same step. Step 1, capital F of x is integral of e to the x dx, which is just e to the x. We don't have to do a substitution. Step 2. I got excited and I forgot what we're supposed to do before we do any of this, and that's use our formal notation. So we hold our pinkies up when we do this. This is formal, like tea time stuff, grandma. Limit b approaches infinity, integral from 5 to b, e to the x dx. So that's our conversion. We're treating this carefully as a limit. Okay, now step 2 is we evaluate on the bounds. Evaluate the antiderivative on the bounds. So capital F at b minus capital F at 5. So that will be e to the b minus e to the 5. Now we're going to take that result and plug it in off the left-hand side. We're going to have the limit of that equals to the limit as b approaches infinity of e to the b minus e to the 5. So this is e to the infinity, which is infinity, minus e to the 5. E to the 5 is 2.7 dot 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 multiplied by itself 5 times, so it isn't that small, but compared to infinity it's pretty small. So small it doesn't do anything to infinity, it's just infinity stays exactly as it is. So that's kind of our answer. But the best answer for a problem like this one is to say that this integral diverges. Which reminds me, I got to go up and fix the missing last step on the top example. So instead of answer, I'll say converges. It's a good final statement. The integral converges to e to the negative 5. Whereas the second one on the bottom, diverges. Oh, I gotta say something about it, even though it's in that video. So this is bad shorthand notation. Bad in quotes won't lead you astray inside this course. Okay, what does e to the minus infinity mean? What does e to the positive infinity mean? So if we took those limits and treated them like evaluations, e to the minus infinity, using the laws of exponents, that means 1 over e to the positive infinity. E to the infinity is e times e times e times e forever, which is infinity. Since e is 2.7, like you're more than doubling something forever. Doubling something forever would give you infinity. More than doubling something forever will give you infinity as well. Now you think about lotteries. 1 in a million odds of winning a lottery is low odds. You're not likely to win. 1 in a billion is worse odds. 1 in a trillion is even worse than that. Well, 1 in infinity is worse than 1 in a trillion. The odds are so low they can't be lower. It's 0 odds. You're not going to win that lottery. Whereas e to the infinity is infinity times e times itself forever. E times e times e forever. Which is going to be infinity since e is larger than 1. It keeps growing. And that result was used in the above one. Hand wavy arguments, but notice that I didn't write that green stuff anywhere in the solution because it doesn't belong there. Go off to the side for your own sake, for your own benefit. If you like writing this type of thing, that's perfectly fine to do. It isn't like a markable thing. It's not something to get marks on. Okay, next question. So it's the same function we did last time. This time the lower bound is where the problem is. So I'm going to convert to a limit. This time, since it's the lower bound, it'll be limit as a approaches minus infinity, and our integral is the integral from a to 3 of e to the x dx. Okay, in the last two examples, one of them converged, one of them diverged. We'll see what happens here. So step 1, capital F of x is the integral of e to the x dx, which is just e to the x. Step 2, evaluate on the bounds. So that would be capital F at the top bound. So capital F of 3 minus capital F of the bottom bound. And that's going to be e to the 3 minus e to the a. And I'll take that result and plug it in over on the left-hand side. So we have limit a approaches minus infinity, and that integral is now going to be replaced by e to the 3 minus e to the a. Okay, next step, when we take the limit, we have something that looks like e to the minus infinity, since we're replacing a with infinity. So limit a approaches minus infinity of e to the a looks like e to the minus infinity, which looks like 1 over e to the positive infinity, which looks like 1 over infinity, which looks like 0. So we get a 0 for the first piece. Well, not the first piece, there's 0 for the second piece. The first piece stays as it is. It's limit of a constant, limit of e to the 3. It's just e to the 3. So e cubed came out, and we would say that this integral converges to e cubed. Okay, next example, we're taking an integral from 2 to infinity of 3 divided by x. So first step, write this as a limit, as this time b is going to infinity. The top bound is the problem, so it gets the infinity treatment, the limit treatment. We're going from 2 to b of 3 over x dx. So step 1, find the antiderivative of 3 over x, which is 3 times ln absolute value of x, plus c, as before we dropped the plus c. Oh, and of course this has a name. This is capital F of x. This is our antiderivative that we're calculating. Step 2, well, I'll put the plus c here and then I explicitly cancel it out because it's been a while since I wrote it. It's going to cancel when we plug in the bounds, so it's not necessary to keep. And all my math prof colleagues are horrified, I think, every time I do that. Right, write the plus c and then cross it out, because something else is going on with definite intervals, but I don't want to get into it. I don't think any of us do, especially with the term the way it is. Step 2, evaluate. The antiderivative on the bounds. So capital F of x on the bounds. So we have capital F of the top bound, capital F of b, minus capital F of 2. So that will be 3 times the ln of b minus 3 times the ln of 2. Okay, now we can plug that in off on the left, limit b approaches infinity, and then put the bracket in, put that purple stuff in here. 3 ln b minus 3 ln 2. Okay, this limit we haven't talked about yet. Not in the review video either, but what is the limit as b approaches infinity of the ln of b? So here's what the graph of the log function looks like. X-axis, y-axis. This is going back a little bit. I think the second week of classes, I looked at the graph of the log function briefly. It looks something like this. One, I should mention that I dropped the absolute value signs because we plugged in b. B is going to infinity, so b is a positive number, and the absolute value is something positive. The absolutes disappear. And then we're plugging in the top bound, or the bottom bound, which is 2, which is positive. So absolute value of positive 2, just the absolute value signs can be dropped. Anyway, so shown in blue here is the graph of ln of x. And it's a function that does grow. The y value keeps increasing as you go to the right, but it grows very slowly. Y goes to infinity as x goes to infinity. So the y value does keep going up. Now what that means is we get 3 times infinity here. We get infinity minus 3 ln 2 which is infinity. So a number did not come out of this. This means the integral diverges. And that's, if this was a test question, one of the options would say diverges. That's what you'd pick. Okay, so getting into some tougher ones. Integral from 0 to infinity of this thing, 12 times x to the power of -3/2. So let's be cautious with, oh, I gotta fix this. I just realized there's a problem with it. Let's change the lower bound. I don't want this to be an issue. Let's change this to a 4. I think. That'll be fine. 4 will be fine. I'm sure. We'll make do if there's a fraction at the end, doesn't matter. Don't think about it, let's do it. Okay, top bound is infinity, so what we'll do is we'll convert this to be a limit as b approaches infinity. Integral from 4 to b, 12x to the -3/2 dx. Okay, step 1. I guess writing the limit is kind of step 0, but it is a step that we should do. Step 1, we want to integrate 12 times x to the -3/2. And the way to do that is to use the anti-power rule. I'll write that down. that the antiderivative of x to the n is 1 over n plus 1 times x to the n plus 1 plus c. So here our n is negative 3 over 2. So negative 3 over 2 plus 1 is negative 3 over 2 plus 2 over 2, which is negative 1 over 2. Making common denominators. So when we take the antiderivative, we'll have 12x to the power of negative 1/2. But more space than that. So x to that power negative 1/2. And then we divide by a 1 over negative 1/2 out front. So that was a calculation for the n plus 1s. Okay, we can clean this up a little bit. We get negative 24, x to the negative 1/2. Dividing by a fraction is the same as multiplying by the reciprocal of the fraction. The minus sign is going to survive, so it's there in front. We have 12 times 2, 24. Then I'm going to do an extra step because we're evaluating this. I'm going to write this as negative 24 divided by positive square root x. So power negative 1/2 means, or power 1/2 means square root, negative power means bringing them to the denominator, put them together, this is what you get. Okay, now step 2. I'll put the plus c and then cross it out at the end there due to the bounds. Okay, step 2. Evaluate this thing, which is capital F of x on the bounds. So we have capital F at the top bound, which is b, minus capital F at the bottom bound, which is thankfully 4 now. You can go back and look at why the 0 had to change with what we're about to do. At least if we didn't want to have some other problem occur for this type of a question. So negative 24 over the square root of b minus negative 24 over the square root of 4 so negative 24 over root b plus 12. Root 4 is 2, minus times minus is positive, so lots of stuff cancels out. And now this is going to go over here. So limit b approaches infinity of, integral's gone. We integrated, we don't need to write the integral again. We've already done that operation. And the result of that operation was this. Okay, I'm going to write down this weird looking step. Limit b approaches infinity of 24 over the square root of b. I know there's a minus sign there, but I don't want to cause clutter. So this is going to end up looking like 24 out of the square root of infinity. Square root of infinity may look odd, but what does square root mean? Square root of a means that blah times blah gives you a. So the answer here is blah equals root a. That statement means that blah times blah gives you a. So we're asking for the square root of infinity, what times what gives you infinity? Well, it's only going to be infinity. And then this is a really bad lottery. Like, this is not 24 in a million, or 24 in a billion, or 24 in a trillion. It's 24 in an infinity odds, which is 0 odds. It's not going to happen. So we have 0 plus 12. We get an answer of 12 from that integral. And I should add this in, almost forgot, it converges. Well, I'm going to flip back and make sure I didn't miss that last one. Okay, diverged, converge, converge there. Okay, we're okay. Okay, now I'm going to do the same thing. I'm going to put a 4 here for the lower bound. I don't want that to be a problem, because right now it is. Is that good enough? It's not good enough. I put an 8 from 8 to infinity. Yeah. We're going from 8 to infinity, 12x to the negative 1/3 dx. So this is equal to the limit as b approaches infinity, integral from 8 to b, 12x to the negative 1/3 dx. We're going to do this in the same sequence as before. We're going to do step 1, find the general antiderivative of 12x to the negative 1/3. We use the anti-power rule, just like the last example. The power goes up by 1. So I'll do that calculation off to the side. Negative 1/3 plus 1 is negative 1/3 plus 3/3, which is positive 2/3. So we have 1 divided by 2/3 times x to the power of 2/3. And then we get a plus c. The plus c can disappear because of the bounds. Okay, and then simplify. This is 12 multiplied by 3/2. So we're going to multiply by the reciprocal. And you're dividing by a fraction. So we get 18 x to the power of 2/3. Okay. Step 2, evaluate on the bounds. So this is capital F of the top bound, so capital F of b minus capital F of 8. So we'll get 18 b to the power of 2/3 minus 18 times 8 to the power of 2/3. So 8 to the 2/3. Power 2/3 means apply the bottom part of the fraction as a root, so cube root in this case of 8, then take that result and raise to the power of 2. That's one order in which you could convert that set of operations into. 18b to the 2/3 minus cube root of 8 is 2. 2 squared is 4. So 18 times 4. Which is 72, I think. 40 plus 32, 72. So 18 b to the 2/3 minus 72. Okay, now we're going to take that result and plug it in. So we have the limit is still hanging around when this b approaches infinity. The integral is gone. We defeated it and replaced it with this. 18 b to the 2/3 minus 72. Okay, now we've got to figure out what's going on with that first part of the limit. So I'm going to separate that off as a side calculation. Limit as b approaches infinity of b to the 2/3. The 18 will just multiply by whatever this is, so let's not carry it with us over here. This is, I'm going to just dispense with the whole limit business. Plug it in. So what does this mean? Well, it means take the cube root of infinity and then square it. So cube root of infinity, what do you multiply by itself 3 times to give you infinity? Like, it ain't 10. 10 times 10 times 10 is not infinity. It's not 100, it's not 1,000 or 1,000,000. The only thing you're going to get that makes it remotely any sense is infinity. Okay, now we have infinity squared, which is again infinity. So it isn't looking too good if what we want to get out of this is a number, because we have infinity minus 72, which is infinity, which means the integral diverges. We don't get an answer out of this. So it looks very similar to the last one. The last one we had power negative 3/2, and this one power negative 1/3. Okay, tougher one, but the same recipe, same procedure, or looks tougher at least. We're going to convert this to a limit as b approaches infinity, integral from 0 to b. I'm going to do this up top because I feel like doing something different afterwards. This is limit b approaches infinity, integral 0 to b, 1 plus 2 times x to the power of negative 4 dx. Let's pretend that it's not formal. So shortcut notation to save writing. Do not use in calculus 1301 or 1501. Please don't do this. You didn't see it from me. Okay, that's the deal. I'm not going to write the limit. I'm just going to do step 1. Find the antiderivative. Find capital F of x equals integral from 0 to infinity. Oh, no, sorry, no bounds. Of 1 plus 2x to the power of negative 4. Okay, and then to solve this, we'll use a method of substitution. I'm going to let u equal 1 plus 2x, the thing inside the bracket, and go from there and see what happens. So du by dx is 0 plus 2. So du is equal to 2 dx. And that means dx is du divided by 2. We'll use that for completing the substitution. So integral of u to the negative 4 and then du over 2. I'll bring the 1/2 outside. Integral u to the negative 4 du, and we can solve this using the anti-power rule. Power goes up by 1, so u to the power of negative 3 since we're adding 1, not subtracting 1, and we divide by the new power, so negative 1/3. And then we can simplify multiplying the fractions together, 1 times 1 and 2 times negative 3. And I might as well put the negative up top. Minus 1 over 6, u to negative 3. And now we undo the substitution. I'll put a plus c and then cancel it, just for the sake of completeness. Keep the balance. Okay, and then when we undo the substitution, replace u by what it was, 1 plus 2x. Okay, step 2. Here's the time-saving step. It just saves writing, and it's not dangerous for the types of indefinite integrals that we have, or the types of improper integrals we have in this course, but it is fairly dangerous to do in general. Evaluate capital F at infinity minus capital F at 0. We're just going to pretend infinity is a number. Actually, before we do that, let's use exponent laws to simplify this expression. So this is minus 1 over 6 times 1 over 1 plus 2x to the positive 3. So a negative exponent can be brought downstairs as a positive exponent. And then clean that up further. This is minus 1 on top, and 6 times 1 plus 2x to the 3 down below. Now we'll evaluate this at infinity. We'll evaluate this at 0. Oh, very bad. Very bad. 1 plus 2 times infinity. 2 times infinity is infinity. And then minus 1 over 6 times 1 plus 2 times 0. 2 times 0 is 0, and I forgot the power 3's. Tack them on now. Power 3, power 3. Okay, let's keep going. 1 plus infinity is infinity, so I have minus 1 on top. And then 6 times infinity on the bottom, that's infinity. And the last second piece, positive from the negative times negative, and we get 1 over 6, since 1 to the 3 is 1. 1 in a million odds, whether or not negative or positive, is going to be 0. No odds. And we get 1 over 6. Converges to 1 over 6 as our answer. Okay, another one. How many more are there? Oh, the absolute value ones. Okay. So next one, and I have to make a comment about this. This is a rough around the edges calculation. We abandoned the limit notation up top. We said, okay, I know you're a limit, but you know what? I'm going to pretend you're not. I'm going to pretend infinity is a number and treat it that way. So my comment here is this is not a good notation. And I'm basically teaching you guys math swearing, like math swear words. That's okay. You know what you're supposed to say, and it's up to you if you're going to say it this way. At least for a multiple choice test. There's no marks for process, but keep in mind if you're going to do this, if you're going to write infinities in this way, then and if you plan on taking more math courses, please drop the habit. It's a bad habit to get into. Okay, next question. Speaking of bad habits not to get into, I'm going to do the same thing. But what we should do is we should write this as the limit as b approaches infinity of the integral from 0 to b of 4x e to negative x squared dx. But let's not continue from that. We'll just leave that hanging out on its own. And we will use shortcut notation instead. Where it is understood capital F of infinity means limit as x approaches infinity of capital F of b. That's what it means. So it's a shorthand for that. Okay, so first step. We're going to calculate the general antiderivative without the bounds. Antiderivative of 4x times e to the negative x squared. And this question is now harder than it was 2 weeks ago. If you were asked this 2 weeks ago, all you knew how to do was substitution. But then earlier this week, or rather later last week, you learned about a method called integration by parts. And then that gave you options, that gave you strategies to think about. So the problem-solving process that I have when I look at an antiderivative is, first I look for anti-chain rule for substitution. So is there a relationship between the different parts of the function? Are they related to each other through a derivative? If you let u equal negative x squared, when you rearrange and get dx, is that going to result in something that cancels out the x inside the 4x? I'm giving you an expression that's completely in terms of the new variable. If so, then use substitution. So say that x on top, the exponent, was not negative x to the 2, say it was negative x to the power of 3, then it would not be a method of substitution question. Anyway, so if we're going to use substitution, substitute with u equals negative x squared. And du by dx is negative 2x. Rearrange and we get dx equals negative du over 2x. Off to the side, I'm going to write down the alternative method that's used. If you don't want to isolate for dx, I want to do it the other way, then we had that du, when we cross multiplied, du is equal to negative, I'll do it in 2 steps, du by dx was negative 2x, so du is equal to negative 2x dx. That means x dx, if I divide, well, I'll just say x dx, divide both sides by negative 2 equals negative du over 2. And then I can replace this x and the dx. So these two pieces together can be replaced by du divided by 2. Or something else along those lines. So instead of dividing both sides by 2, what if you multiply, multiply both sides by negative 2, so you have negative 2 du is equal to 4x dx, and then replace the 4x dx with negative 2u du. It'll work out to be the same, no matter which method you use. So in the substitution, I did not change the 4x, it is as it is. I did replace the x, negative x squared with a u. And then the dx, it's getting replaced by negative du over 2x. And we can rejoice. The x cancel. Part of the constant cancels. Now that that's too crucial, 4 divided by 2 is 2. The negative will go up front, so negative 2. Integral e to the u du. Antiderivative of e to the u is just e to the u plus c. But we can eliminate the plus c through the bounds. And finally undo the substitution, so 2e to the negative x squared. Now step 2, evaluate on bounds. With this shorthand. Use limit shorthand. So that's going to be capital F at infinity minus capital F at 0. So negative 2e to the negative infinity squared. Keeping in mind that the negative sign is outside the squaring operation. Only the infinity is being squared, not the negative. Then minus negative 2e to the negative 0 squared. And again, it doesn't really matter here since it's 0, but that's not, that negative there is not being squared either. So negative 2e to the minus infinity, since infinity times infinity is infinity, plus 2e to the 0, since 0 times 0 is 0. E to the minus infinity is 0. E to the 0 is 1. So 0 plus 2. We get 2 as our answer. We can say the integral converges to 2. And e to the minus infinity, so the thing that turned into a 0, is 1 over e to the positive infinity using laws of exponents, which is 1 over infinity, which is 0. So, reasoning that you shouldn't write. Not needed or necessarily wanted. Okay. And that's it for the regular part of the lesson. I'm going to make a third video that contains 2 more example types that we're not going to test on the exam, and then a discussion of some of the meaning that's hiding behind the indefinite integrals, at least in their connection to area from section 6.5.